Today I am going to discuss about NMR spectroscopy for third BSc students of our college, Kadir College, Adarampattina. This topic is present in Physical Chemistry 2 paper for BSc students. This line shows the syllabus related with this topic, NMR spectroscopy. This syllabus is a part of Unit 5 of Physical Chemistry 2 for third BSc students or under our university, Bharathasan University. Now the Unit 5 spectroscopy to 5.3 NMR spectroscopy, nuclear spin and conditions for a molecule to give rise to NMR spectrum, theory of NMR spectra, number of NMR signals, equivalent and non-equivalent protons. In NMR spectroscopy, there are number of concepts, but in this syllabus, limited concepts are given. That is NMR spectroscopy, theory of NMR spectroscopy, and conditions for a molecule to give rise to NMR spectrum, and a number of NMR signals, equivalent and non-equivalent protons. So a very limited topic. So that is very simple. So questions are asked in this topic. This slide shows a request to viewers. NMR spectroscopy, that is nuclear magnetic resonance spectroscopy. The spectroscopy is due to nucleus of an atom. All the nuclei cannot give NMR spectrum. So this slide shows conditions for a molecule to give rise to NMR spectrum. That is NMR active nuclei. So odd number of protons, even number of neutrons. That is nucleus with odd number of protons, even number of neutrons, or even number of protons, odd number of neutrons can give the NMR spectroscopy. That is these nuclei with odd number of protons, even number of neutrons, or even number of protons with odd number of neutrons. These nuclei are NMR active. For example, for odd number of protons with even number of neutrons, there are number of examples. One example is H1. H1, that is atomic number is 1. That is atomic number means number of protons or number of electrons. So on considering the nucleus atomic number, that is number of protons. So H1, that is atomic number is 1, so it contains 1 proton, and the mass number is also 1, so 1 minus 1, that is 0, so it contains 0 neutron. So H1 is an example for odd even type. So 1 proton, 0 neutron, 0 is considered as the even number. So H1, that is odd even type. Similarly, another nucleus, boron 11, and here atomic number is 5 and mass number is 11. So 11 minus 5, that is 6. So boron 11, B11, nucleus contains 5 protons and 6 neutrons. So this is also another example for odd even type. Another example is fluorine 19. Atomic number of fluorine is 9. It contains 9 proton and 19 minus 9, 10. That is 10 neutrons. So it is an example for odd even type. Another example, phosphorus 31, and atomic number of phosphorus, that is 15, and mass number 31 here. So 31 minus 15, 16, that is 16 neutrons. So phosphorus 31, the nucleus of phosphorus 31 contains 15 protons and 16 neutrons. That is another example for odd even type. Similarly, even number of protons with the odd number of neutrons, that nucleus is also NMR active. There are a number of examples. An example for this type, even with odd, there is even odd type, there is C13. C13, in the case of C13, atomic number is 6, that means it contains 6 protons. And the mass number, in the case of C13, mass number is 13, 13 minus 6, 7 neutrons. So this is an example for even odd type. That is, the C13 consists of, nucleus consists of 6 protons and 7 neutrons. This type of nucleus is also NMR active. That is odd even type or even odd type. All the nuclei are the NMR active. These are the various examples for NMR active nuclei. That is H1, B11, fluorine 19, phosphorus 31, C13. But the nucleus with odd and odd, that is odd number of proton with odd number of neutron, that is NMR inactive. Similarly, even number of protons with the even number of neutrons, that is also NMR inactive. So NMR inactive nuclei, example H2. H2 here atomic number is 1 and but mass number is 2. So it consists of the nucleus of H2 consists of one proton and one neutron. There is 2 minus 1, that is 1. So it consists of one neutron. So odd order type. And another example for even type, that is C12. C12 atomic number is 6, that means it contains 6 protons. And C12 the mass number is 12. So 12 minus 6, that is 6, that is the nucleus consists of 6 neutrons. So C12 consists of 6 protons and 6 neutrons. This is an example for even type. So even type, odd type nuclei are NMR inactive. So suppose question may be asked, which among the following is NMR active, by giving number of atom, that is H1, B11, H2, C12, C13, etc. For that, the atomic number and the mass number of the atomic number is subtracted from mass number, that gives number of neutrons. Atomic number gives number of protons by uh, simply noting the odd and even type and even odd type, that nuclei are number active. Suppose the nuclei are odd and odd or even and even, then that type of nucleus is NMR inactive. Now, spectroscopy means study of interaction of electromagnetic radiation with the matter. And spectrometer means that is the instrument used for the above study, above spectroscopy study. And spectra means the data obtained from the instrument in the form of graph. That is the output of the instrument, that is called, is in the form of a graph, that is called spectrum. The output obtained from NMR spectrometer, it is called NMR spectrum. Next, theory of NMR spectra. So NMR is, that is absorption spectroscopy, and absorption takes place in radio frequency when spinning nuclei is placed in a magnetic field. That is, NMR spectroscopy is a spectroscopy involving transmission of spinning nuclei with I value, that is half of atom in a molecule in magnetic field by absorption of radio frequency region. A spin of proton, hydrogen nucleus. Hydrogen nucleus is otherwise called as proton because the nucleus contains only proton. So it is called as simply it is proton. Hydrogen nucleus, that is otherwise called as proton. And spin of proton, that is equal to half, just like electron. Proton also have spin, that is the spin of proton is half, and spin angular momentum of proton, that is mi value, that is plus half or minus half. That is spin if it is in clockwise direction, then the spin angular momentum, that is plus half. If it is anti-clockwise direction, then the spin angular momentum is minus half. So in the absence of magnetic field, both these two states are degenerate. That means both are having same energy. Mi is equal to plus half, mi is equal to minus half. The level with these values, mi plus half minus half values, and these two levels are energy levels are degenerate. That means both are having same energy. But in the presence of magnetic field, the degeneracy is lost. That is, one having lower energy, another having higher energy. That is mi is equal to plus half. That spin, that it is, if it is aligned with external magnetic field, then it has a lower energy, and another one is minus half, that is opposite to magnetic field, and it has higher in energy. So in the presence of magnetic field, we have two levels, with one level with the mi plus half, that level has lower energy, and mi minus half, which has higher energy. So we have two levels. In the absence of magnetic field, Mi is equal to plus half and Mi is equal to minus half. These two levels have the same energy, that is given in the diagram. And in the presence of external applied magnetic field, these two levels are split into two. One level having lower energy, that is Mi is equal to plus half, that has lower energy, that is aligned with the applied magnetic field, and Mi is equal to minus half, that is that level has higher energy, that is opposed to magnetic field. And also the direction of applied magnetic field with the spin states, that is given, spin plus half aligned, spin minus half, that is opposed. Now the energy difference between these two levels, that is lower level, upper level, that is delta E, I already told the NMR spectroscopy is absorption spectroscopy. Therefore, E absorbed that is equal to E minus upstate, that is upper level energy minus lower level energy minus E plus half state, that is equal to delta E, difference in energy according to Planck's equation, that is equal to h nu. Let this equation be 1, and the delta E is the energy difference between the two spin states. Mi is equal to plus half and Mi is equal to minus half level. And but the delta E value, that is the function of applied magnetic field strength. That is the stronger the applied magnetic field, the greater the energy difference between the spin states, that is delta E. So that is delta E is equal to 2 mu h h0. Let this equation be 2, and here mu h, that is the magnetic moment of proton, and comparing equations 1 and 2 we get h nu is equal to 2 mu h h0, and from this equation we can derive nu is equal to 2 mu h h0 divided by small h, where small h is the Planck's constant, and h0, that is the strength of applied magnetic field. Nu is related to applied magnetic field strength by this equation. Nu is equal to 2 mu h h0 divided by h. Here small h Planck's constant, mu h magnetic moment of proton, h0 that is strength of applied magnetic field, and nu is the frequency of absorption. Now this equation shows the resonance absorption frequency varies with magnetic field. Thus, by varying magnetic field strength, one can measure the absorption frequency nu, which can cause tension of nuclei between two levels, that is from lower level to upper level, that is Mi is equal to plus half level to Mi is equal to minus half level, which gives NMR spectrum as shown below. The NMR spectrum of a proton, that is given this slide. These are about theory behind NMR spectroscopy. Next topic, number of NMR signals, equivalent and non-equivalent protons. In this slide, there are 14 serial number, 14 examples, 14 molecules, and first one, serial number 1, methane, which gives one signal due to 4 equivalent protons. The methane molecule contains 4 equivalent protons, so it gives only one signal. And serial number 2, molecule is CH3, it contains 2 methyl group, but all the protons are equivalent, so it gives one signal. But in the case of serial number 3, methanol, it contains two types of proton. One is methyl proton, another one is OH proton, so it gives two signals with the intensity ratio A is to B, that is equal to 3 is to 1. And in the case of serial number 4, CH3, CH2OH, it gives three signals with the intensity ratio A is to B is to C, that is equal to 3 is to 2 is to 1. 3 is due to methyl proton, 2 is due to methylene proton, and 1 is due to OH proton. So another case, serial number 5, that is CH3, CH2, CH2OH, it gives 4 signals, and due to 4 types of protons, methyl proton. Another one is methylene proton adjacent to methyl group. Another one is methylene proton adjacent to OH, and the last one OH proton. So it gives 4 signals with intensity ratio A is to B is to C is to D, that is equal to 3 is to 2 is to 2 is to 1. For understanding first type, A proton is in black color, and B proton is red color, and C proton in green color, and D proton is in violet color. So A, B, C, D for a different color and the intensity ratio. In this case, 3 is to 2 is to 2 is to 1. And another case, serial number 6, this case it contains two types of protons, two methyl groups are equivalent, and two methylene group, these two are equivalent, so it gives two signals and two peaks, and intensity ratio A is to B, that is equal to 6 is to 4, otherwise that is 3 is to 2. Similarly, another case, CH3, CH2, CH3 contains two methyl group and one methylene group, and the two methyl groups are equivalent, electronically, environmentally equivalent. So that is, it gives total it gives two signals, that is CH3 group gives one signal, and methylene group gives another signal, but two methyl groups are equivalent, so it gives two signals with intensity ratio A is to B, that is equal to 6 is to 2. 6 means that is a total number of methyl proton, two methyl group, so the intensity ratio is C6, and for the case of methylene, that contains 2 protons, so 6 is to 2. And serial number 8, that is the molecule is C6H5CH2 CHO. It contains 3 types of proton. One is phenyl proton, another one is methylene proton, another one is aldehyde proton. So this molecule gives 3 signals. The intensity ratio A is to B is to C. That is equal to 5 is to 2 is to 1. Another case, in the case number 9, it gives 3 signals and 1 signal is due to 2 phenyl groups. 2 phenyl group and another one is methine CH proton. Another one is aldehyde proton. So it gives 3 signals. The intensity ratio A is to B is to C is equal to 10 is to 1 is to 1. 10 is due to 2 phenyl groups, 2 phenyl group protons. And serial number 10, it contains 2 methyl group. 2 methyl groups are equivalent, and methane proton, there is another type, and acid proton, there is another type. So it gives 3 signals. The intensity ratio A is to B is to C, that is equal to 6 is to 1 is to 1. 6 is due to 2 methyl group, 2 protons of 2 methyl group. And serial number 11, it gives 1 signal due to the presence of 4 methyl group, all are equivalent, so it gives 1 signal. And serial number 12, it gives 2 signals due to 3 methyl group, and that is 3 methyl groups are equivalent, and methane proton, that is another type. So it gives 2 signals. The intensity ratio A is to B, that is equal to 9 is to 1. 9 is due to 3 methyl group, that is the protons of 3 methyl group. And in the case of 13, this case it gives 2 signals. Here 2 methylene group are equivalent and one methylene group, that is B, that is different. So it gives 2 signals. The intensity ratio A is to B, that is equal to 4 is to 2. Otherwise, it is 2 is to 1. And serial number 14, this molecule contains 3 types of proton. This methyl proton CH3, that is one type. Methylene proton CH2, that is another type. And methoxy proton, that is another type. It gives 3 signals with the intensity ratio A is to B is to C, that is equal to 3 is to 2 is to 3. These are about equivalent and non-equivalent protons and number of signals for various molecules, various types of molecules. This slide also shows the number of signals for various compounds. In the case of first compound, it gives 2 signals and 2 methyl, it contains 2 equivalent methyl group, and it contains 2 methylene group. That methyl groups are denoted by letter A and methylene groups are denoted by letter B, because of 2 signals, and here the intensity ratio A is to B, that is equal to 6 is to 4. And in the case of second compound, it contains 3 types of protons, and it gives 3 signals, and 2 methyl groups are equivalent, and then the intensity ratio 6, and 1 methane proton, it gives intensity 1, and aldehyde proton gives intensity 1. So A is to B is to C, that is equal to 6 is to 1 is to 1. In the third case, it contains 3 types of protons, and 1 methyl proton adjacent to methylene proton, that is A, and a methylene proton, that is B. Another methyl proton that is adjacent to CO group, that is another type. So the intensity ratio is A is to B is to C, that is equal to 3 is to 2 is to 3. This compound gives 3 signals. Another compound, fourth compound, it gives 3 signals. It contains 2 equivalent methyl group and 1 methane group, that is denoted by letter B, and COH acid proton is given by the symbol C. So it gives 3 signals, 3 types of protons. The intensity ratio A is to B is to C, that is equal to 6 is to 1 is to 1. And the last one, it is the spectrum of ethanol. It contains 3 types of protons. That gives 3 signals, and A, HA, that is one type, HB another type, HC another type. That is a methyl proton one type, methylene proton another type, OH proton another type. It gives 3 signals. The intensity ratio A is to B is to C, that is equal to 3 is to 2 is to 1. With this, I want to conclude my lecture on NMR spectroscopy for third BSc student on the basis of syllabus. I think this presentation is more useful for third BSc students, and the syllabus is very limited in the NMR spectroscopy, but questions are asked in this topic, like which among the following nuclei are NMR active, explain the theory of NMR spectroscopy, and find out the number of signals obtained for the following molecules. Similar questions are asked, and I think this is very useful for UG students. I express my sincere thanks to all viewers. Thank you, one and all.